Hello and welcome to Tom Talks. Today we're going to continue on with our front wing interactions video. Now I've done one of these before, so if you enjoy this one, maybe you'd like to check that out. But the general goal behind the video is to analyse some of the interactions that the front wings on open wheel race cars have seen over the years. And today we're going to focus mainly on front wing strakes, but also going to be looking at some of the front wing upper interactions. So I've prepared a geometry which is a little bit more complex than last time and should indicate some of these flow features quite nicely. Again, I really like these interactions, so I'm quite looking forward to getting over there and having a good crunch at the CFD, and I hope you enjoy the video. Alright, so before we get into it, let's have a quick little look at our geometries. Okay, so on the right hand side we've got our base, and on the left hand side we've got our updated geometry. Now as you can see on the base we've just got a simple footplate and a little tunnel system on the 3-element wing there, and as we come inboard we flatten off and then go into our Y250. And then on the updated case, if I come right in here, we've got the exact same template that we're running with. We've got a foot plate there, but we've actually added an M plate here with a canard on it on the side, and we've got some vertical turning vanes there, and we've also got 2 fences there. So we've got an outboard fence and we've got an inboard fence there as well, or strake, whatever you really want to call it. So let's have a look at the CFD. Now, I feel that this geometry is going to illustrate some of the interactions that I want to show. So although it might not look perfectly what you're normal used to, the flow features should still be quite similar. So firstly, let's look at coefficient of total pressure on the base geometry here. So sweeping through in X, which is starting from the front and moving backwards through. Okay, so as we go through, we generate some loss off the footplate itself, and this is rolling up into our vortex, which is going to be going in this tunnel section. And as we proceed, you can see it expands, blows up quite large. And then we get into the interactions of the tyre here, and you'll notice in this case we've got a lot of clean high energy air here, and this is going to want to come down. The tyre is going to downwash it, and it's going to push a lot of this loss out the sides and squirt it out quite a lot, because we haven't pushed much air over the tyre. Because we're with quite a conservative wing, it's not actually that big. Okay, so let's continue. Coming in, as you can see, we pushed some of it out and we're beginning to squirt out a bit there on the side. So out of here, we'll continue on. Nothing too bad with the squirt there, and there we are behind the wing. Okay. Now let's have a look quickly at a brief overview of our updated case. So firstly, we've already got a little bit of a blow here, which is unfortunate. However, we'll still see some of the effects. Now we're also generating a vortex off the canard. This is an edge without an end fence on it, so it's very easy for the air to loop around, and we're going to generate quite a powerful little vortex here. We should also note that we've got the end plate, so this loss in this region is typically going to be smaller, but we've also got this supporting strake, which I have had a quick look at the CFD before I've done this, and I think that the supporting strake is a bit too far inboard. Nevertheless, we'll carry on. So as we move through, you can see that this strake, this supporting strake, the outboard fence here, I do have quite a bit of a curvature to it. because naturally the flow is going to want to come under and it's looping around something like this. So by curving that, you can minimize your losses from it, because the point of this strake is really a supporting role to really manage this loss as it blows into the front tire, and not to spill inboard too much. This strake, on the other hand, is very different. It's got an outwashing profile to it, and this is the outwashing profile is there to generate a powerful vortex, mainly off the bottom side of it. And what this is going to do is we're going to try use this to deal with our tire squirt a bit more effectively. And the reason why this strake is outwashing is because it's in a position of the wing where there's really not a lot of lateral movement of the air. So this is something that we really need to consider. Some categories, so I'll draw out a front wing here. It's got a bit of curvature on the end there. Maybe we've got an element right there. So some categories can run their wings very low to the ground. And if they're very low to the ground, we're going to make a lot of low pressure underneath the wings. So we're going to have a lot of air which wants to come inboard like this. So you could have quite straight fences there, and you're still going to generate a very powerful vortex off them, because the relative flow vector hitting the strake is still at quite a high angle of attack. Now let's consider the other side. Let's say that we're in a wing where it's not as close to the ground, for example, and we've got not as low a coefficient of pressure underneath, or we're in a section of wing where maybe the outside section is backed off, maybe the inside section is backed off, and we're right in the middle, then we're going to have less flow coming from the outside and less flow coming from the inside. So our net flow is going to be straight ahead. Or sorry, I should have said we might have flow coming from the outside, we might have flow coming from the inside, but we're in a much more balanced situation. So in this scenario, it might actually be more ideal to give our strakes a curve so that we can roll up a vortex off them, because we don't have that lateral inwash or potentially lateral outwash to play with to generate our vortices for us. So just because you see a strake that's very curvy doesn't mean that the strake is working the airflow that hard. The strake could be there just minimizing losses, and it could actually be conformed perfectly to what the CPT field actually looks like. Anyway, let's continue. So we can begin to see some of the interaction between this vortex and this one here. Now you will notice that the canard vortex there has gotten quite lossy. I think that's because of maybe the M plate vortex. I haven't done sweeps in my report detailed enough in my script, but I think that that'll be from maybe the back side of the M plate, or potentially some sharp edges which are flicking up a little bit of loss, and we're losing some performance there. Regardless, we're still going to see the interaction that I wanted to see. So I'll be honest, I've always thought about our turning vanes on the front wing, so this structure that we create, and this one, the canard, I kind of think of them as, I've always thought of them as two different structures. So the turning vanes, we can send them up onto the upper part of the tire, and I've heard from somebody I've talked to that you can actually churn up the boundary layer on the top of the tire and thereby reduce separation, so your wake is going to be better. So I kind of left it at that, and I was always just thinking about that. But one of the cool YouTube videos out there, which I'm sure a lot of people have seen, is the one where Willem is talking about the Y250 Vortex. And he specifically mentions multiple times how the turning vanes are co-rotating with the Y250, but the outboard M plate is counter-rotating. and I've always sort of brushed this off like, yeah, of course it's counter-rotating, but I never thought about the implications of that. So the reason I created this geometry the way it is, well, firstly, it's illegal because I've gotten rid of a large portion of end plate. If I bring up the model again, I've gotten rid of a large portion of end plate here, and if I was to have a guess, for these types of front wings, so around 2018, the last of the very complex front wings, I'd have it a guess that if teams could, they'd probably remove some parts of their end plate as well. I think it's mainly there for sponsorship material, and that's why the rules have a prescribed area and also a cross section so that you have to fill a certain area as well in the rules. So why have I done this? Well, I'm trying to interact these with this, and I've cut out this section here because we're dealing with our counter-rotating vortices. So I'll come back onto the CFD. Now if I draw it out like this, we've got our turning vane vortices, which should have all merged together. In this case, I got a bit greedy. In the effort to try and make the effect powerful, I put in lots of turning vanes. Usually you iterate 1, 2, 3 and develop the system, but I got a bit greedy. It's not perfect, however it's still worth the interaction, and this canard goes like this. Now these are counter-rotating, so there's a central part in the middle where they're both working together, and what this can do is take a lot of the flow from here and pull it straight through that gap like that. So with this system, if we work the canard vortices together, or in this case our canard vortex and our turning vane vortex together, we can effectively squeeze some air in between and shove it up and out of the way of the front tire, and this could be an effective means of generating outwash. And this is what's happening in this example. Whether that's what the Formula 1 teams were doing or thinking in 2018, I'm not sure, but I think it's a rather cool theory. I've got a photo of a Formula 1 front wing at the end, so we can dissect maybe why this wasn't the case. Anyway, let's continue on. So as you can see, we've developed quite a loss coming in from the footplate here. You can also see that our strake here has shed a top vortex because of our outwash. Now, this isn't ideal if we can't really control it. This is going to get sucked up by the front wing there. It would be really nice if we could keep this vortex traveling with this vortex and create that same effect to laterally expand the airflow outboard without the cost of balance if we were to just cut down our inboard section front wing to get lateral that way. So that would be really nice. I'm not sure if that's possible, to be honest. Not looked at that too much. But to minimize the loss of this top vortex, we could have perhaps reshaped our strake something like that. So the bottom outwashes a lot, but the top doesn't. So perhaps we wouldn't have generated such a loss off the top when it's not actually going to be doing much. The purpose again of this strake was to support this structure here, which we can compare more to the other wing. But generally the strake was designed to not make too much loss behind it, too much disruption, and that's why it was curved the way it was, and that seems to be doing its job. Now we've got this blow up here, and we're going to feed this directly onto the front of the tire. So we'll continue down. Now you can see this vortex, our straight vortex, our main straight vortex off the bottom, is already beginning, if I go back a bit, it's beginning to move upwards. And it's beginning to move upwards because of the viscosity effects from the Y250. The Y250 is obviously just it looks quite small on your screen, but you forget how much of the flow field is actually moving around. So the Y250 can tend to give you nice lateral expansion down low, so you can work out some of your lower tire wake quite well, but it tends to pull the upper wake up and over the top, and this can be detrimental in a full car simulation setting. So that's something quite cool to notice here. We've also got our canard vortex going strong, quite outboard. Now we're not going to see the full effects of this because we're dealing with a simplified wheel geometry. So we've got no ducting, and we've got not the realistic turbulence that we'd normally see where air could actually pass through the wheel. Anyway, for what we're looking at, it was perfectly fine. Let's continue. Now, similar to before, we've got our mass flow here. It's working to push some of the loss out of the way, not necessarily a good thing, because it's going to squirt our loss out of the sides. Okay, so we've got some very defined structures here. That's our bottom strake, which has been kicked up quite high, and we've got our canards still, and now we're beginning to get some squirt out the side. Okay, let's continue. We've got progressively more squirt, and we're back behind our tire. Interesting little effect there with the straight vortex, you can see. This is indicating perhaps some attachment, or a bit of attachment somewhat around the back of the tire, pulling the wake outboard a bit, but we'll have to check with some other contours. And we have that. So now we should really compare our two cases and see the major differences in the flow field. Okay, so firstly, a coefficient of pressure over body. Now here's our base, here's our updated. Base, updated, base, updated. Okay, so some things to note there is some of the acceleration around the outside edge of the tire. Okay, we've also got a change in coefficient of pressure here, right there, and by the looks of it, a change in high pressure ram right there, and it also looked like there was some sort of a structure there before. Alright, so something like that. Now, with our update, you can see that we've got a more, this is the part that I'm really looking at, we've got an extended, really, really low pressure region here. Now, you can't make a perfect assumption about this, so we'll, firstly, when we've got an area of really high curvature, like around the front edge of the wheel, and a very low pressure on it, we can usually say that there's some flow, some flow passing over that outboard edge, but we need to remember that because it's creating such a low pressure, it's likely to be quite high energy flow. So just because there isn't a low pressure on a curved surface doesn't mean that air isn't passing over it. It could just be very, very lossy air, and so we're not seeing the full effect. Now let's compare our coefficient of total pressure between the two cases and perhaps see some better changes. Okay, so base and update, base, update, base, and update. So yes, incredibly different so far. We can see that firstly the loss here looks to be more inboard than the other case. So let's check. So our update, yes, so it's definitely much more inboard. Now, I'd say that a good reason or a good chunk of this will be from the front wing end plate, but you will probably also see some lateral support from that strake, the support strake, the outboard strake that I put in. You might also see some support from this vortex, or these vortices, washing air off the strake and in, although this would be really quite slight itself. Also, with the strakes and the position that they are, sometimes you can get quite a good seal from them and generate a bit more localized load on your surfaces. In this case, I actually dropped a bit of load. This means that the underside of your front wing has a relatively higher coefficient of pressure, which means you're going to be sucking in less air, and this could also be a reason why we've got that loss less inboard and more outboard. So flicking through again, we can see our upper management is definitely beginning to pull some of this air up and outboard, especially compared to our original, and so we're already beginning to validate what we think the geometry is doing, especially having seen our coefficient of pressure on the outboard section of the wheel. So let's continue down. So just a bit later, we see pretty similar effects. Now our loss has been contained outboard a bit from our front wing footplate, and we're kicking up even more mass flow with our upper wake management there. Now I'm gonna skip back a bit more to our wheel. So here's our base and here's our updated. Okay, so quite big differences now in the flow field. So we've got our upper straight vortex here, which is not very desirable in this case, I don't think. It's quite high and out of it. This system is pushing air laterally onto the tire here, which is probably why we saw that big kick in CPO earlier before, that big kick outboard, but hard to say right now. The lower vortex is in much more of a position to begin working with the squirt here. Hopefully not drawing it in too much because it is quite high off the ground, but actually adding some momentum this way and potentially dealing with this squirt coming up and outboard. And that's what I think is happening here compared to our original case. We can't analyze our canard too much again because simplified wheel geometry. Let's flick here. Yeah, so you can see now it does look kind of evident that our lower straight vortex is helping with our squirt. We do have to remember though that our loss from the front wing footplate was laterally going to move in further to fill the void behind the front wing, which was more effective, but also originally we just saw how much further it was in, so it doesn't really matter the reason behind it. It was always inboard a little bit more, so that could also be a reason why we're kicking up a bit more squirt in that particular place. Okay, a bit further back, base and update. Similar again, now our updated case has kicked up a little bit more squirt this time, but it is being drawn in between these two systems here, so in between the Y250 and the straight vortex. You can already see the way that it's passing in like this. So for a more optimized geometry, if you were to give this a second iteration, you'd definitely try to look at moving this straight vortex perhaps a little bit lower. Okay, now behind the tire now, and you can see quite a large difference there. So we're kicking a lot more of the flow with this vortex, it looks like. Maybe a bit more flow attachment around the tire. This vortex is looking to work some of that flow outboard a little bit, perhaps due to flow attachment around the back of the tire. Maybe not, maybe we're in a bit of a transient situation and we haven't accurately modeled the problem. I'm not sure. We have made some relatively big changes, so I think that we can make some general assumptions, but we still need to be careful. Alright, now if we look from top view, so just off the contact patch, here's our base, here's our update, base, update, base, and update. We can see, yes, we have kicked out a fair amount of air in that region compared to before. So generally speaking, this is a good thing. We can see our outboard profile if you wanted to look at it a bit more closely, and you can see how the loss works around the front tire, what goes outboard and how much goes inboard, relatively speaking. You can also see the geometry of our strakes, very aggressive on the inboard strake fence right there. Okay, so generally the geometry has done what I wanted it to do. We set up this counter-rotating vortex pair on just above the front wing main plane to achieve some outwash, which we could see, and also use the strake to limit some of the tire squirt coming out and better manage the wake in that region. So as always, I like to think about the contours that you can use to show the major differences, so we can perhaps know how to iterate the geometry further in a more efficient manner. Now, I talked about in the last part how we can begin to look at a vortex breakdown by looking at your velocity, not just magnitude, but your velocity in different components. And in this scenario, it would be my favorite tool to analyze what we're changing and where we're changing it in the flow field. So last time we looked at velocity in X, so into the page or out of the page. This time we're dealing with a lot of upwashy, downwashy vortices. So I'd actually look at velocity in my up and down, which is Z. So I'll show you that. Now, unfortunately, my camera turned off and I actually lost the last part of the recording yesterday, but I'm here to do it again. Okay, so here's our base case, and as we can see, everything's quite normal and, well, really as we'd expect. So we've got a lot of upwash here, a lot of downwash there, a lot of upwash here, a bit of downwash there, and a fair amount of downwash there. So basically everywhere we've got a vortex we can see this quite clearly, and so we know that the core is going to be in the middle, and you can begin to get an idea of the angular velocity. So we're getting a lot of velocity here and a lot less there, but we're still getting some upwash in that region. Okay, so as mentioned, this is a really good contour when you're adding things like strakes or any sort of vortex anywhere, because you can see both sides of the vortex, what's going up, what's going down, and then specifically place these vortices where you need to get that velocity where you want it to be. So let's have a look at our updated case. And completely different. So I'll sweep through for you. Here's our base, update, base, update. So incredibly different flow fields, just as we'd expect. And it's great that it's so different, because it means that it's easier to design upon and iterate on, because we've got a really effective way of reviewing our results. So what do we notice? Well, firstly, here is our straight vortex. So we've got an upwashing side here, and we've got a downwashing side there. Now that's normal, and that's what we'd expect. We can see this vortex here, which is the same as the last case. But if I flick, you know, it's a much smaller magnitude, which is, again, as we'd expect, because we discussed there were multiple reasons why perhaps we were getting less in-wash in through here. One being maybe that we added the end plate, and that's made a bit of a change. Now, I'd say that one of the more important interactions that we're seeing here is what's going on in this region. So I'll draw out our geometry. We have a turning vanes around about here, and we've spun up our vortices like this, and we had a canard coming out here, and or a dive plane, whatever you want to call it, and we've spun up the vortex this way. So that should be a bit further out, sorry. But what we can now see is this counter-rotating vortex pair system that we've set up on the front wing. So we've got our turning vane, which is producing upwash here and downwash here, and we've got our canard, which is producing its upwash here and its downwash here. These should really be directly up or down because that's what our velocity is, but we can still see what's going on. So in this area here, we're now chucking air all the way up and outboard, and this is what's giving us our outwash and a little bit of upwash as well, to push air around the tyre so we can shove some of that weight a bit further outboard and we'll be better off for it downstream. So that's a really neat way to see where we're actually putting these vortices and how much interaction we're getting between them. Another really good way is to use LIC or streamlines or oil lines, whatever you really want to call them. And so we can see very easily here, here's our first vortex and we're pushing air this way. And here's our second vortex and it's taking air out like this. So generally we're doing exactly what we wanted to do. Now we've got our other turning vane vortex here, or one of the other ones. This is not helping us at all. We're probably robbing the powerful turning vane vortices of a bit more power because we've placed one in front even though it's lower. That's me just being a bit greedy with the geometry there. Could have built up into it a bit more. Now we can also see that we're beginning to get our straight vortex. It's not at full strength yet, but I've also got another shot here where we're much closer to the tyre, so we're actually a centre line tyre, and here is our bottom strake vortex. And you can begin to see its influence on the squirt. So it's providing quite a large downwashing component here, and it's providing an upwashing component here, which is why the squirt was moving around the way it was. You can also see how big the flow field is that the Y250 is creating. And that's why we get a little bit of lateral support out of the Y250. Now, as promised, I do have an image of a 2018 front wing, courtesy of motorsport.com. Now, I wanted to show you why perhaps this interaction is happening or not happening. Okay, so, well, firstly, we can notice we've got these cascade elements here. And these are going to be powering up this vortex even stronger. And that's just because we're ramming up high pressure in this section. So our vortex off here is going to be a lot stronger. Comparatively, we've backed off the section near the end fence, so that's going to be a smaller vortex, but the takeaway I think is that they're trying to not produce a vortex that way, because that would be counter-rotating to this vortex and in quite close proximity. So that's probably a good reason why they're doing that. Now you've also got your dive planes or canards down here, and they will produce a vortex, and they look like they'll combine together and head quite low, but it's dependent on how much the elements on the front wing here, what they're doing with the airflow, how high is that going or how low is this going, if we're going to see the interaction that I thought that we maybe would see. So you've also got this inboard canard, which is what a lot of the teams ran. This is going to shed a co-rotating structure here. Now it is also going to shed a vortex that way as well. The reason we know it's going to shed a vortex this way is because it's a higher angle of attack than the outboard canard, and it's closer to the top of the end plate. So this is going to win out essentially the war, and we will get a counter-rotating structure. Obviously this is going to be a lot smaller than the inboard structure right next to it. That's going to be a lot stronger because there's no end fence there to stop the vortex production. But generally, the reason why this interaction wouldn't be happening is because we've got this big end plate here, and the canards are so low down, and these vortices on the turning vanes are so high up. So perhaps that's why this interaction is not happening. One more thing while we're here, the turning vanes here, you can see they're very, very sharp. So these are shedding off quite a nice vortex themselves. You can really tune your loss with how sharp an edge is. You'll also notice that the McLaren here doesn't have it, but in the footplate region right there, so in the footplate region there, sometimes they have a flat extension and they actually chamfer it up, so it's quite sharp on the end, and in some years they've actually curved it up like that. So you can directly affect your vortex creation like that. One more thing to note are the leading edges on the turning vanes. These will be especially useful in cases of yaw, so we don't encounter separation, and the devices, you'll also be able to crank them at a bit higher of an angle of attack. I didn't have actual airfoil profiles. Mine were all assuming like just a 3mm piece of carbon fiber, so we lose quite a lot of performance there. But I think that we still got the airflow trends that we wanted to see. So in general, I think that our simulations were successful. Okay, so thank you for watching this video. I had some fun making it, and I think the geometry is quite cool. It's a shame that I don't have the computing power all the time right now to do a full case, but still, I think that we got to go through some quite cool interactions so far. As always, if there's something that I said that was wrong, I'd love you to let me know, that way I can learn more. Or if there's a better way of doing stuff, I'd love to know as well. So other than that, I'll see you in the next video.